Lesson 6.1, Temperature and Thermal Expansion. Common temperature scales. There's several different scales we use to measure temperature. The most widely used one is the Celsius or the centigrade scale. And on it, water freezes at 0 degrees Celsius and water boils at 100 degrees Celsius. So there's 100 degrees between freezing and boiling, hence it's centigrade. In the U.S., we use the Fahrenheit scale, where water freezes at 32 degrees Fahrenheit and boils at 212 degrees Fahrenheit. To convert, temperature in Celsius is 5 nines times the temperature in Fahrenheit minus 32. The Kelvin scale, notice it's not degrees Kelvin like it's degrees Celsius or degrees Fahrenheit. It's just Kelvin. 0 Kelvin is absolute zero. The temperature cannot be less than that. No temperature can be less than that. And 273.15 Kelvin is water freezing. And 373.15 Kelvin is water boiling. So the width of a scale in Kelvin, width of 1 Kelvin, is the same as 1 degree Celsius. But Kelvin is adjusted to start at 0 at absolute zero. No temperature can get less than absolute zero. So to convert, your temperature in Kelvin is your temperature in Celsius plus 273.15. So let's convert 30 degrees Celsius to degrees Fahrenheit and Kelvin. Our temperature in Celsius is 5 nines. The temperature in Fahrenheit minus 32. So we have our 30 degrees Celsius there. So multiply by 9/5. And we get 54. And add the 32. When we add the 32, we get 86 degrees Fahrenheit. To find the Kelvin, temperature in Kelvin is your temperature in Celsius plus 273.15. So our temperature in Kelvin is 30 plus 273.15. So that appears to be 303.15 Kelvin. In physics, we will use degrees Celsius and Kelvin. Probably never use degrees Fahrenheit in physics because it doesn't fit well with the other units. For heat, heat always flows from a hotter object to a colder object until we're in thermal equilibrium, which means that the temperatures are the same. So it goes from hot to cold until the temperatures are the same. The zeroth law of thermodynamics says if A and B are in equilibrium and B and C are in equilibrium, then A and C are in equilibrium. So if everything's the same temperature, there's no heat flowing. In normal solids, how would you open a glass jar if the metal lid is too tight? Well, simple way is you run the lid under hot water. As the lid is run off under hot water, the lid expands as the temperature increases, and it expands faster than the glass. So eventually the lid becomes loose and you can just take it off easily. That's an example of thermal expansion. Works in all three dimensions, but we can talk about it in each of the sets of dimensions. Linear expansion would be expansion in one dimension as the temperature changes. And your change in length is your linear expansion coefficient times the original length times the change in temperature. So that change in temperature can be in degrees Celsius or Kelvin. And the unit for the length really doesn't matter. Even small changes in your length can have serious consequences. So have you ever looked at a bridge as you're coming onto a bridge and seen an expansion joint? So that's an example of the expansion joint. Notice you have this gap here. So as the bridge gets hotter and expands, it can slide into that gap. There's another example. As the bridge gets hotter and expands, the road gets longer and actually comes together there in that gap. Another example. And another example. It's not a broken bridge with that gap. It's just so as the bridge gets hotter, it has a place to expand. Or here were railroad tracks. Got too hot, they expanded, had no place to go, so they bumped sideways. Let's say a steel bridge is 2 kilometers long. If the temperature when it was built was 20 degrees Celsius, what length expansion joints are needed to prevent buckling at 43 degrees Celsius when it's much hotter? Well, our change in length is the coefficient times the original length times the change in temperature. We want to know the change in length. Well, if you look in your book or your notes, you should see that steel has an expansion coefficient of 12 times 10 to the negative 6 degrees Celsius to the negative 1. Our original length was 2 kilometers, so that would be 2,000 meters. And our change in temperature, well, we're going to be at 43, and we started at 21. It's always final minus initial. And then you can multiply all that together. And your expansion joints need to be a little over half a meter long. Other examples are the bimetallic strip. It's made from 2 strips of metal that have different coefficients of linear expansion. One side expands more than the other side. So here with the brass and steel, when it's heated, the brass expands more. Since it expands more, it has to get longer, and so it's bent and bends around the steel. As it gets colder, it will get shorter, so it bends the other way. They can't slide past each other because they're attached to each other, so it has to bend. And that is used in automatic switches, like in thermostats, where it's based on temperature. If we're talking 2 dimensions, area thermal expansion is approximately 2 times the coefficient of linear expansion. And volume thermal expansion, they gave it a different coefficient, but it's usually close to 3 times the linear expansion. So why do fluids in a car usually have a big reservoir tank? Like the radiator, the brake fluid, power steering fluid, and oil, and so on. Well, the engine gets hot, so all these liquids get hot. So as the fluids heat, the volume increases. So we need to have some place for the extra fluid to go. Otherwise, it'll burst your pipes and hosing and everything. And you can't leave it less, because then when your engine's cold, there's not enough fluid to do anything. water is unique in that the volume will decrease from 0 to 4 degrees Celsius. Usually, as things get warmer, the volume increases, except for water. So as water is at ice, the volume actually gets smaller until it hits 4 degrees Celsius. Then the water expands from 4 degrees Celsius and up. And this is due to the polar molecule in the water. The water is densest or least expanded at 4 degrees Celsius. So as the weather gets cold, the lake water cools, and because it's more dense, as it shrinks, it sinks down to the bottom because it's more dense, and the warmer water, which is more expanded, is less dense, it moves up to the top. After all the water is 4 degrees Celsius, the top starts to freeze. But because the 0 degrees Celsius water at the top is less dense than the 4 degrees Celsius water below it, the ice in the cold water floats at the top. So the ice floats and provides insulation for the warmer water underneath of it, so it does not freeze solid until it gets really, really, really cold. And this allows all the little frogs and fishes and everything in your lakes and ponds to survive winter. Interesting how the most important molecule for life, water, is this very unique special property, almost like it was designed. That's it for this lesson. Have a good day.